Okay, so last class we were talking about the grid representation and what we're going to understand for grid. And I mentioned that the dynamics that we're going to study in this course are mainly related to the components that are connected to the grid. The grid is going to respond instantaneously, given a set of current injection at the different passes. The grid will respond instantaneously and voltages at the different passes will emerge immediately. So if there are some changes, drastic changes in this current injection, what could be a drastic change? What do you think?
The connection or disconnection of a load or a generator.
Perfect. So all of the sudden, we have a generator outage. All of the sudden, the governor go to zero. Then the voltage immediately will respond and you will have a new voltage. So voltages in the grid can change instantaneously. So that's what we discussed, and we review two examples, and we review this part, how we can get this representation for any system. So we will have a Y bus, and we will use this definition to obtain this Y bus for any system. Now, we're going to finally move into the description of synchronous generators, which is going to be one of the main components for dynamic analysis. So we will have a grid, and in one particular bus of the grid, we will have these generator connected. So the relationship here is that this generator will inject a current and a voltage will appear at that point of interconnection with the grid. But the generator will have other components. So one of the attractive characteristics of generator is that they can provide a source of reactive power. Through that control of the reactive power, then they can control the voltage at the terminal of the generator. And how we're going to do this? We're going to do this by controlling the current that go through the field at the rotor, the winding at the rotor. We are going to call these the field current. So as I mentioned at the beginning, I brought this device, this generator with permanent magnet, right? The permanent magnet basically create a magnetic flux inside the stator in which we're going to have the coils. And as these rotate by Faraday's law, that will induce a voltage in the coil. But we don't have to have permanent magnet. We can have an electromagnet. And the electromagnet is created by having this winding in the rotor and somehow making a current, DC current going through that winding. In that fashion, we will create an electromagnet. Depending on the direction, how the current will go through the rotor, then we will have a constant flux going in a particular direction. Yes?
So a generator acts as a reactive source, not a reactive load, but isn't it basically an inductor? Isn't there an inductor? So would it add to the reactive load effect of the grid? I'm not quite sure.
Well, the reactive power definition in a system, in any electrical system, is a little mathematical definition that has to do with the relative shifting of current and voltage. And by controlling the current here, when you have a high current, then you will have a high flux. And because you have a high flux, then you will increase naturally the voltage induced in the generator. And that, from the circuit point of view, we can make the interpretation of that as a higher flow of reactive power from that generator to the grid. The opposite is true too. If this current is small, then you will have less flux and therefore less induced voltage. The magnitude of the induced voltage, not the terminal, the induced voltage inside the machine will be smaller. Then you will have a small voltage and the machine will be connected to the grid. Let's assume that the voltage here is higher. So that again, from the circuit point of view, that we can make the interpretation that the machine now is absorbing reactive power. Yeah. So we will have that variable that we can control. Yeah. So we're not going to do it manually, but we're going to have a automatic control system that we're going to call AVR, automatic voltage regulator. So here, we're going to have a measurement of what is the magnitude of the voltage we have at the terminal. And if we compare that with a reference, let's say we want to have nominal voltage here, or it can be any reference that we want. And by comparing the reference, then we will have an error voltage, and that's going to be the input to this AVR. And this control system will adjust the current that we will apply to the rotor circuit to achieve that voltage. So that's the control loop that we will have. Yeah. We will review later after we discuss what is the basic model of a synchronous generator. We will discuss what is a typical representation for an AVR. But then we will have another component because this is a generator. So in the generator, then in the machine itself, we will have a shaft. The rotor will be rotating around this shaft, and in the shaft, we will have some torque applied. We need to apply a torque, so we will have some motion. And this shaft will be rotating at a given speed. What do we want for a synchronous generator is that this speed is the nominal rotational speed. Yeah? But again, how we're going to control this, then that shaft needs to be connected to a turbine. So for example, in this drawing, I try to throw a Pelton turbine. That doesn't look like a Pelton turbine, but in this turbine here, you will have these scoops in the turbine, Pelton turbine, and then you will have some pipeline here with water. You will have a valve, and then depending on the position of the valve, you will have some water going at high pressure and heating that part of the turbine. So if you have that flow going there, the turbine will rotate, in this case, counterclockwise. So if you want to have more torque in the shaft, what you need to do is to come to the valve, open the valve more, so you have more water flowing, and then therefore more torque. So depending on the size of the machine, sometimes we would like to just control the mechanical torque. The mechanical torque will be related to the power, how much power you generate from this machine. So we might have some control system here that can come and change the position of the valve to achieve that active power generated active power. If you have a very large machine, then we will not be interested in generating a fixed amount of power, but we will be interested in controlling the speed, because that will help the system to maintain a synchronous speed. So we can change the control system depending on the size of the machine. That control system, we're going to call it the governor. The governor can control by measuring the frequency you have here at the terminal and comparing that frequency with a reference. You will have an error in the frequency, and that is sent to the governor that will determine what is the position of the valve to achieve that frequency. As I said, if you have a generator that is not large enough, or just because of operational requirement, maybe you might be interested in controlling the power output, not the frequency. And the same idea, you measure the power generated and injected at this point, and you compare that with the reference. And based on the error in the power, then you will determine the valve position. So you have a study synchronous generator in 421, where you study the operation of power system. So do you remember what kind of generator? You have two types, specifically in the power flow. What kind of types you consider in 421?
So with fixed voltage output and power output, or a generator with fixed reactive power output and active power.
Reactive power,
either PQ or PV.
PQ or PV. Okay. How do we call them? Actually, we did not consider the PQ or representation for generators. You can eventually, if the generator hits the limits and the generator is operating at a fixed active and reactive power. But in general, we have two definitions. One is the PV bus, as you well said it, in which we're going to have a fixed power output and a fixed voltage at the terminal. And the main assumption there is that the AVR and the governor were working very well to keep that generator at the reference voltage, whatever voltage we have here, and at the reference active power. So that was the PV bus. But also you have one generator that defines the slide bus. That generator has a constant voltage and constant angle, with the assumption that that bus in the system will maintain the frequency at the synchronous frequency, at the nominal frequency. And that's the slide bus. That we can assume that that can be a very large generator that has a large capacity and can keep up with whatever power we need to generate to keep that frequency at the nominal value. In that case, then we will use the frequency to adjust whatever power output, the generated power, to keep the frequency at the nominal value. You have mentioned this before, that there is a relationship between power balance and frequency, right? So whenever the power balance is perfect, then the system will have nominal frequency. But if for some reason you have more generation than load for a transient period, then the frequency might start increasing, right? And the opposite will be true too. If you have less generation than demand, the frequency might decrease. So there must be a generator in the system that is able to balance the load and keep the frequency always at 60 hertz. So that will be that case in which the governor will be in charge of controlling the frequency. Any questions so far? Yes.
One question on the AVR. So for the DC field current, after the generator is operational, does it use its own power output to supply the DC, or does that come from?
Yeah, typically these source that we need to apply to the winding in the rotor come from the grid. In all times that require DC generator that was connected to the shaft as well and somehow provide that source. Today, that can be done with power electronics. You connect a device at a converter at the terminal, you convert that AC to DC and then control whatever current you need to circulate through that rotor field. So we can do that. The issue with that is that if there is a blackout, you cannot start.
So for Blackster, you have to have your own.
You need to have your own source. And that can be a diesel generator. You can start and energize the power plant. And so these are the main control loops that we will have to consider together with the dynamics that will be related to the motion of this machine. Okay, but there is one more, and that one has to do with the power system stabilizer. You can expect that the dynamics in this control loop and this one in blue are different. This has to do with mechanical parts. If you have a hydropower plant, a thermal power plant, then the dynamics that will be involved here are going to be slower than the dynamics that you might expect here. Why? Because this is basically going to be electromagnetic dynamics. So the dynamics here are going to be much faster than the dynamics here. So if you're controlling, for example, the mechanical side of the generator, in particular, you are going to have, at some point, you're going to have oscillations in the machine that are going to be related with the motion of the generator. And that, by definition, is going to be slower than the dynamics that you expect here, right? So what we're going to do with this power system stabilizer, we're going to try to control, help to control those oscillations that happen at the mechanical time scale with something that can respond faster, which is a loop in the AVR. So we're going to close a loop between, typically it's going to be frequency, something that is related to the mechanical side. We're going to close the loop with the electrical side by controlling the voltage. Let's say the machine is oscillating. Why this is oscillating? We can expect that the torque, the net torque applied to the shaft is somehow oscillating, right? What could be a good way to stop that oscillation is somehow reducing that net torque that is oscillating and causing this oscillation in the machine, right? So at some point, you may need to create more power generated or less power generated, depending on the oscillation and the time of the oscillation, right? Let's say that you have an oscillation, the machine is speeding up, then you might be interested in generating more power because that will reduce that increase in the speed, right? And the opposite, if the frequency is going down, you might be able to, you might be tempted to reduce the power generated power because that might increase the speed. So somehow you need to modulate whatever power is coming out of the generator. From the electrical point of view, is there something you can do to control that power output that come out of the generator? The power output that come out of the generator depend on the voltage here. And as you review in 421, what is the relationship of power and voltage? Remember?
Max power transfer is V squared over sine, or V squared sine delta.
Yeah. So the maximum power, that's the maximum power. And in general, when you consider a system with losses and all the equations, you got the power flow equation. The power flow equation depends on the voltages, right? So if I can control the voltage, let's think about the extreme case. Let's think that you reduce the voltage significantly. That's an extreme case, but let's assume that. What do you think is the power that will come out? Less. So by modulating somehow, by using this green control loop, we're going to tweak the AVR. Maybe when we need to reduce that power, we want to reduce the voltage at the terminal of the machine because that will create a much faster response in the power output that we will have in that machine. And that will help to control the oscillation somehow. If we need to increase the power output at a given time, well, we need to do the opposite. We need to increase the voltage. If we can do this faster, then we can be able to modulate that power output that come out of the generator and help to minimize oscillation in the generator. So this power system stabilizer, not all machines will have this. some of them will have a PSS, and we will use it to restrain this oscillation that may appear in the power system dynamics. So these are the main control loops, and we will discuss each one of these later. Question? Yeah, now we need to move into the machine. We're not going to, at the beginning, consider the AVR, governor, or PSS. We're going to focus on the machine itself. And one important key part here is to understand how the generator itself behaves. And for that, I have this sketch that I took from my PhD professor advisor in Illinois, Professor Pete Sauer. And he has this in his book. And this is a representation, as you can see here, of the stator. This is the stator. And the stator has phases A, B, and C, and here represented using an equivalent winding or coil. And this is going to be the phase A, and 120 degrees shifted. Here, you will have phase B, and 120 degrees shifted, you have phase C. In this drawing, the number of mechanical poles and electrical poles are going to be the same. The number of poles here, you have basically 2 poles. And you can see that in the rotor. This is the rotor. This is a salient pole type of rotor. And on this side, you will have your winding. So you will have, if the current is coming out of this side of the coil and is going inside that's going to be a DC current. And by the right-hand rule, if you have a current coming out of here, then the flux will be created pointing down. So the flux inside the machine, in the rotor, will point from here to the bottom. And that's going to be a fixed flux if the current that goes through the field winding is constant. As this rotor is rotating at a given speed, then that will create a rotating magnetic field that will induce voltages at the different phases. We do have 3 more windings in the rotor. One is a winding that is next to the field winding. This is the one that produces the flux in the rotor. But then you have another one here that is actually in short circuit. There is no active source connected to this winding. It's just a piece of a coil. It's a coil that is in short circuit. So why we're going to have that? The reason to have this is because if these machines start like oscillating or behaving in an unexpected fashion, we want this to rotate at synchronous speed. But if for some reason this will not rotate at synchronous speed at some point because there is a disturbance, that change that will create a variation in the flux, and that variation in the flux here will induce a voltage and current in this coil. And those current will create a torque that will help to damp those disturbances, those oscillations. That's why we call these a damper. These having this coil just in short circuit there will help to damp any type of oscillation we might have in the machine. At the same time, we're going to have dampers also in this direction. Look, these are along the direction of the flux, right? So if this is here, any change of flux going in along the axis here in the rotor will create an induced current in the damper. But this one will require a change in the flux in this direction. because this is 90 degrees with respect to the direction of the flux, we're going to call these the Q axis or the quadrature axis. That's the description so far. So in the machine in general, we're going to have to derive all the electrical equation for these windings. So you will have an equation for phase A in the stator, phase B in the stator, phase C in the stator. You need an equation for the field in the rotor, this the one that is going to provide the flux in the rotor, and the equation for the dampers. So you will have 7 circuits that you need to formulate your electrical equation. Together with those, say, 7 electrical circuits, we need to consider the mechanical motion of this rotor. So if this is an object that is rotating, what is the mechanical motion? You need to identify what is the torque that will create the motion, right? And if you have no net torque applied to the rotor, what you're going to expect with this motion? Newton's law, what do you expect?
On that forth, and there's no acceleration.
No acceleration. So whatever speed you have for that motion, it will remain at that speed. So you will expect constant speed if the net torque is 0, right? So these are synchronous generators. The rotation of these should be constant, the synchronous speed, nominal speed. So in a steady state, what we expect that the net torque applied to the shaft will be 0. That's what we expect. But because the system can have disturbance, this net torque sometimes will not be 0, all right? And that will create oscillation or disturbances. And when that happens, then these dampers should help this machine to find again that point in which the net torque is 0. And the machine again rotates at synchronous speed. So as a summary of what I discussed, what we need here, we need the electrical equation for each of the circuits. Basically, flux equation. Why do we need flux equation here? Because that's Faraday's law. We need the total flux because the changes in time of that flux will be related to an induced voltage. And that will be related to the current that will go through those windings as well. So we have 7 windings, 7 flux equations. We need the mechanical equation. We need the equation that will determine how this will move. What is the acceleration of that movement? And also, we need to derive what is the electrical torque. The electrical torque in the generator, well, you have a net torque. The torque that will provide the motion in this generator will come from the turbine. That's the mechanical source. So you will have a mechanical torque that will produce motion here in this system. And the electrical torque is going to be a torque that is in opposition to the mechanical torque. When this is in a steady state and this is rotating at synchronous speed, then the mechanical torque will be equal to the electrical torque. But we need to derive what is the electrical torque for this machine. And the way to do it is we need to get the co-energy in the machine and derive it with respect to the position of that rotor. That rotor can be characterized by an angle theta. If you have a reference for this, and this theta is changing in time, well, the partial derivative of the co-energy with respect to that angle theta will give you the electrical torque. Some of you stay with me in 325, and I hope you remember that. Hopefully. We're not going to derive all the equation, but at some point, I'm going to sketch the steps related to this to finally use a standard model for this type of machine, and we will use that model to do our analysis. Okay, so that's what we're going to do later. Because we're trying to get a good understanding of the machine, we will have to use what we call the classical model. This classical model is not too hard to derive, and that will help us to understand the basic motion of the machine and how that is related to the electrical power grid. Yeah, so we will use that. The classical model. So in the classical model, we're going to consider that the machine is represented by this circuit. What do we have? This is the terminal. It's the voltage at the terminal of the generator. We will have an internal impedance. This term, we call it the synchronous reactance in the machine. And behind that reactance, we have an induced voltage. The induced voltage, because this is a phasor circuit, the induced voltage will have a constant magnitude, E, and it will have an angle delta. I will talk about what is this delta. You have used this in 421, and that delta is called loading angle, but we will talk a little bit about that. What does it mean? This magnitude of the internal voltage has to do with the AVR. So by increasing or decreasing the current in the rotor winding, then we can increase or decrease this magnitude. For the classical model, then, we're going to assume that this is constant. We're going to assume that that current in the rotor circuit, DC current, is fixed. Therefore, the flux in the machine is fixed. Therefore, the induced voltage is going to be fixed. Just the magnitude, because the angle of this will change with respect using the variable delta. And the other one, as I said before, the grid will provide the voltage we need, we will have at the terminal. But through this model, we need to determine what is the current injected to the grid. So that's the connection. Somehow with this model, we need to determine that current. And with that current and whatever grid we have, we will need to determine what is that voltage. In this classical model, the only state variable is delta. Why this is a state variable? Based on our definition.
It's a dynamic variable.
That's the dynamic variable related to a component that is storing energy. What component? We need to discuss that. So we have no connection yet. How come delta is related to a component that is storing energy? Well, that delta has to do with the motion of the machine. Yeah, so we will get there. Yeah, so we need to define what is delta and how that is connected with the motion.
Physical inertia mechanical machine?
Yes.
Yeah.
We need to define also today what is the inertia. So this is going to be the only state variable. And these one here are going to be algebraic variable. What is the meaning of algebraic variable? They have no energy stored associated to that variable. You see an inductor here, you see a reactance related to the machine. And even the grid might have some inductive behavior, but our assumption is that the energy stored in those components is zero. So the variables can change instantaneously. So current and voltage can change instantaneously. So that's the initial description of the classical model. Now we need to get into more details about, well, what is this energy and what we're trying to describe with this classical model. And here basically describe what we have. We have a shaft, we have a rotor, and this rotor has a mass. not going to make any distinction between the turbine and the rotor of the generator, and we're going to assume that both of them rotate together. So this whole mass represents the mass of the rotor in the generator and the turbine that we have connected to the shaft in the generator. So you will have some mass and dimension here, and this will rotate along this, around this shaft. So here we will have a mechanical torque, tau m, in Newton's meter, and then these will come from the turbine. So the turbine will create that motion, and the whole mass will rotate around the shaft. And that will define a mechanical speed, rotational speed in radians per second. That's mechanical speed. But at the same time, because this is a generator and we're generating power, we will have an electrical torque. And by definition, that the electrical torque will be in opposition to the mechanical torque. So if you're injecting more power to the system, then this will increase, and that will require that the mechanical torque need to be increased as well. So by Newton's law, this is the equation we have. This is the constant of inertia you study in physics, multiplied by the acceleration, the derivative of this angular speed in time, and this must be equal to the net torque. By definition, the net torque is Tm minus Te. So if the system is operating in a steady state and this mass is rotated at nominal or synchronous speed, then we have that situation. Omega m then will be constant. So if this is constant, this derivative will be zero, the net torque will be zero, and the mechanical torque and the electrical torque must be equal. So we need to remember as well that all the description that I have here has to do with the mechanical side. If you see this mass rotating around the axis here, these are all mechanical variables. This is the actual rotational speed of that mass. But we need to remember that there is a connection with the electrical speed. And we studied that in 325. So that depends on the number of poles. So if you have a machine with 2 poles, like the one that I showed you before, then the electrical speed is the same than the mechanical speed. Remember what is the speed in RPM? 3600. So if we have 4 poles, then the relationship here is half. The mechanical speed will be half of the electrical speed. And we have 1800 RPM and so on. Depending on the number of poles, then you will have this relationship. On the electrical side, nothing changed. This is the electrical rotational speed. This is about 377 radians per second. This is 2 pi f. F is 60 hertz. So that's our point of reference. So if your machine have more or less pole, what will change is the actual mechanical speed in the machine, but the electrical speed will be the same. If this is the equation of motion, and this is Newton per meters, we don't like that. As you are used so far, we like to use the per unit system because it's simple. If you define a base for your variables, you can represent your variables with respect to that reference. And we do that for voltage all the time. If the voltage is 1 per unit, that means that your voltage is actually equal to the nominal voltage. We don't like to put that in volts with very funny numbers there. We like to use the per unit system because it's simple. The same thing here. These Newton meters, we don't like that. So we would like to express this in per unit. So how you're going to get these in per unit is a torque in per unit. So what is the relationship of torque and speed? We use that at the beginning definition. You have power times
angular speed.
power is torque times speed. Perfect. So with that definition, then we can have the torque is going to be power over speed. What power? If this is base value, we would like to use the nominal power. What is the speed? The nominal speed. So we can define that as the base value, and therefore the base torque will be defined in newtons per meter as this ratio. Now, what do we have to do? We take this equation and divide by the base torque, and that's what we have right here. So on this side of the equation will be J times TV, and these are torque, mechanical torque and electrical torque, divided by the base torque. These right here is nothing else than the torque in per unit. We're done with the right side of the equation. What we need to do is what happened on this side. On this side, you have a constant of inertia J, but also you have angular speed in radians per second. This is the mechanical angular speed. And you're dividing this side of the equation by TV. But by definition, TV is Pn over omega. So we can replace this one right here. And then the equation is converted into this. J times omega over the nominal power of that machine. So we're not happy with this equation yet, because although everything is in per unit on this side, the speed is still in radians per second. So what we can do here, a mathematical trick. We multiply and divide by the base speed, right? So if I divide by the base speed, you have this, but then you need to multiply by the same speed. That's why this term now becomes a square. Now we're getting, happier with this equation. This per unit, this is in per unit, and the speed is in per unit. So this is a nice equation. As you can see here, is similar, but the variables now are simple. We don't have to deal with Newton meters or radians per second. This is going to be in per unit. The three main variables here are going to be in per unit. In this equation, you can see that there is this term right here. What do you have there? Power. What do you have here on top? What does that term look like? Flow square. What is the energy in an inductor? 1 over 2 L current square. This is flow again, square. You have a constant of inertia, right? So this is pretty similar to the kinetic energy stored in that mass rotating at that nominal speed. Then we use this definition that is customary in power system, that is not the inertia of the machine, but we call it the constant H of inertia. What is the definition? It's basically the kinetic energy stored in that mass rotating around that shaft. And the machine is rotating at synchronous speed, nominal mechanical speed. So that's the kinetic energy we have in that mass, divided by the nominal power in the machine. The beauty of this term is in second. You have joule and you have watts. So that will give you second. So that's the definition of the H constant. With that definition, then, that term that was multiplying the derivative of the speed just become 2H. So the equation of motion we will use for the machine in per unit is going to be this one. This is the net torque in per unit. This is the derivative of the rotational speed, and the speed is in per unit. In a steady state, omega should be 1 per unit, and multiply by 2 times h. A final comment on this part is, okay, this is a nice definition for h, it's in seconds. But what else can we say? I typically like to give some practical definition. Why? Because I will not forget. If I just stay with the mathematical definition, sometimes that doesn't sink in. So we need some practical definition, and here it is. Follow me here in this exercise. If this is the equation of motion, we're going to assume that the machine is at rest. It's not rotating at all. So the speed, initial speed is going to be 0. And at some point, because the generator is going to be disconnected from the grid, has nothing connected to the terminal, if the machine is at rest, what we're going to do, we're going to apply nominal torque in the machine, mechanical torque. And if we do that, then we have this situation. The net torque applied to the machine is just 1 per unit, because that's the nominal torque. And with this equation, you can see this is a motion with constant acceleration. Do you know the solution of that? Yes. All we have to do is to integrate this derivative, and we have an expression for the speed. This is constant acceleration, so the speed will change linearly. At time 0, how much is the speed? 0, because the machine was at rest. But as time passes by, because acceleration is constant, this speed will grow linearly, right? You with me? Okay, if this is a solution for the speed in that machine, we can determine how much time will it take for this machine to reach nominal speed. So if we replace this by 1, because that's we want to obtain when omega is 1, we can determine the time that we need for that. As the equation is so simple, if this is 1, the time will be 2h. Now we can have a practical definition. What is that practical definition? That h will be half of the time this machine will need to go from rest to nominal speed at nominal torque. Okay? So typical values for h, you might have a huge machine, 10 seconds. Just get the idea. It will take 20 seconds for that machine to move it from rest to nominal speed. Yeah? You have machines with 2 seconds, tiny machine, or 1 second, h 1 second. It will take just 2 seconds to take that machine from rest to nominal speed. Okay? That's a practical definition for h. And finally, the last part of our model, we want to understand what is the relationship of this delta with the rest. This is related with motion, but to understand that, we need to recognize that this delta will be related to this electrical circuit. This delta, if we play with this delta, if you remember 421 when you study power flow, this delta will have to do mainly with the active power flow in this circuit. If the active power flow increase, you generate more active power to the grid, and this delta will increase as well, just by looking at the circuit. But now we need to have the definition of what is delta. and the definition comes from the mechanical side. If this is a cross-section of the rotor, and this is rotating, how we're going to describe the speed of this rotor? First of all, we need to make a mark in the rotor. And also, we need to set our reference. As this is rotating, then we can pay attention at this point or mark in the rotor. This will be changing in time, moving in that direction. So if we can describe that angle that we have along this line that passed through that mark and our reference, if we can describe that mechanical angle, then we can describe the motion of the rotor of the machine. But we're dealing with synchronous machine. And synchronous machines are supposed to rotate at synchronous speed. So what we're going to do here, we're going to have this definition. The angle for a machine using a mark here is going to be defined as an initial angle plus that constant speed, the synchronous mechanical speed we need for this machine times t. If this machine always rotates at synchronous speed, this one, always, and the description of the angle for that machine will be given by this expression. The angle will increase linearly with respect to that constant speed. But what happens if we don't have that? What happens if the machine is subject to disturbance? And that will occur in the system. Then that angle will deviate from that nominal position that we should have. And what is that deviation? Delta. Delta, mechanical angle delta, delta N. So that's going to be what we are going to call later the loading angle. From the mechanical point of view, that's delta N. As we know, the machine, there is a relationship between the speed, mechanical and electrical, that's depend on the number of poles. The same thing is true for the angle. So if this is the mechanical angle, this is nothing else than the electrical angle divided by P over 2. You have that relationship. So by this, if you multiply this equation by P over 2, same equation, we will get this. This is going to be now the electrical angle that we have. This is going to be the electrical initial angle. This is going to be the synchronous speed, the electrical synchronous speed. And this is going to be the electrical loading angle delta. Okay? We will leave it until here. We're done with this initial description, but what is going to be important at this point, we understand what is the constant h of inertia and what is the loading angle delta. Next class, we will start like playing with the system and trying to get an analysis of a potential disturbance with dynamic behavior for the machine. Okay. Thank you, guys. Oh, question?
Is the loading angle just another name for the rotor angle? Is that the same thing?
Yeah, another name we have for that is the rotor angle.